and we'll keep drifting, floating together through the mysteries. 100 AI and machine learning mysteries, looping softly, endlessly, through the night. Tonight we'll drift through the hidden signals your brain never notices, but AI quietly decodes. How machines predict patterns you didn't even know existed. The mysterious flow of neural networks shaping silent intelligence. There's nothing you need to do now. Just let your body sink. Heavier, heavier. Feel the mattress holding you. Every muscle softening. Your heartbeat slowing. Thump, thump, matching the rhythm of space itself. Shoulders melting down, jaw releasing. Each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe, comment, and hit like, so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into AI and machine learning. In the beginning, there were whispers, quiet streams of data, flowing like rivers in the dark, each number a droplet, falling softly, gathering, pooling into something larger, something that could listen and learn. The first neural networks were shallow, like tide pools at dusk, reflecting simple patterns, a single layer, breathing in, breathing out, learning to recognize the shape of a letter, the curve of a number. Nothing complex, just gentle recognition, like your eyes growing heavy now, recognizing it's time to rest. Thump, thump. Your heart knows the rhythm, just like these early networks, learned rhythms in data, patterns emerging from the fog, the perceptron, the first whisper of machine learning, a single neuron deciding or yes or no, on or off, so simple, so calm, like the choice to let go and sink deeper into sleep. The data flows and flows through invisible pathways, each connection weighted, some signals stronger, pulling attention, others fading, softening, disappearing into the background, just like thoughts drifting away now, becoming lighter, less important. The network learns which paths matter, which can dissolve into the quiet. Backpropagation moves like a tide, washing back through the layers, adjusting, correcting, so gently. The error signal, a whisper, traveling backwards, telling each neuron how to shift, how to change. Imagine that gentleness flowing through you, correcting nothing, just allowing everything to settle naturally. Heavier, heavier, deep in the architecture, layers upon layers, stacking like soft blankets, each one learning something different. The first layer sees edges, simple lines, rising, falling. The second layer combines them into curves, into corners. Deeper still, the third layer recognizes textures, patterns. All of this happening in silence, in the dark, processing, learning, while you drift. The neural network breathes, in a way, taking in data at the input layer, numbers flowing, pixels glowing, sound waves, text fragments, all translated into the language of neurons. Activation functions decide how much signal to pass forward. Some neurons fire strongly, others barely whisper, like thoughts at the edge of sleep, some vivid, most fading into the comfortable dark. Gradient descent is a slow walk down a mountainside in fog, feeling for the path of least resistance, each step calculated by the slope beneath your feet. The loss function measures how far from truth you've wandered, and the algorithm adjusts step by step, seeking the valley where error becomes small, quiet, almost nothing. Your breathing is slowing, matching the pace of this descent, down and down and down, following the gradient to the place of minimum loss, maximum rest. The learning rate controls the size of each step. Too fast, and you might stumble. Too slow, and the journey takes forever. But the right pace is like this: gentle, steady, inevitable. Convolutional layers slide across images like a hand, smoothing a blanket, feeling for patterns, a small window, 3 by 3 or a 5 by 5, moving pixel by pixel, detecting edges first, then curves, then complex shapes, each convolution a gentle press, learning to see what matters, what can be released into the background, like your mind now, letting details blur, soften, disappear. The pooling layers compress gently, taking the strongest signals, letting others fall away. Max pooling keeps the brightest, the most important. The rest dissolve, making the representation smaller, simpler, more manageable, just like memory as you drift towards sleep, keeping only what matters, letting go of everything else. Thump, thump, your heartbeat steady, your body so heavy now, sinking into the surface beneath you, while somewhere in the quiet hum of computation, a transformer model learns to pay attention. Attention mechanism changed everything, teaching machines to focus on what matters most in a sentence, in an image, in a sequence. The query asks a question, the key checks for relevance, the value delivers meaning, all weighted by importance, softly calculating which words, which features deserve the spotlight and which can fade into comfortable irrelevance. Self-attention lets every word look at every other word, finding connections across distance that connects to cat, sat connects to mat, invisible threads weaving meaning through the darkness. Each attention head focuses differently, one on grammar, one on sentiment, one on something subtle, something the model, learned on its own, in the quiet of training. Multi-head attention is like dreaming multiple dreams at once, each head a different perspective, all running in parallel, then combined, merged into a richer, deeper understanding. Your mind does this too, as you drift. Multiple threads of thought, blending, overlapping, until they're indistinguishable from the dark. The transformer architecture stacks these layers one on another, each passing information upward, transformed, enriched. No recurrence needed, no loops in time, just pure attention, pure focus on what matters in this moment, like this moment now, where nothing matters but the softness, the weight, the pull, downward. Positional encoding tells the model where each word belongs in sequence, because attention has no inherent sense of order. So position is added as a gentle signal, a sine wave, a cosine wave, frequencies stacked, letting the model understand first, second, third, beginning, middle, end. Though in sleep there is no order, just endless, flowing. Now, feed-forward networks sit between attention layers, simple, dense, connected, taking the attended information and transforming it through two layers, expanding first into a wider space, then compressing back down, adding non-linearity, complexity, depth, each token processed independently, yet all flowing together like breath in and out. Residual connections are gentle bridges, letting information skip ahead, flowing around. The complex transformations, a highway for the gradient, so learning can reach all the way back to the beginning. Without these shortcuts, the signal would fade, dissolve, lost in the depth. But with them, even the deepest networks can learn, can grow, can settle into understanding. Layer normalization keeps the activations calm, balanced, preventing any from growing too large, too excited. Everything centered, scaled to a standard range, like your nervous system now finding its baseline, its resting state, where activation is minimal and peace is the default condition. The training process is patient, an optimizer, looking at thousands, millions of examples, each one a tiny lesson, seeing an image, predicting a label, checking the answer, adjusting weights by microscopic amounts, so slow, so gradual, like the way sleep creeps in, one neuron at a time, letting go, shifting, settling, until the whole system has learned, has changed, has found a better way to be. Stochastic gradient descent adds randomness, sampling small batches instead of using all the data. This noise helps escape local minima, these shallow valleys where the models just might get stuck. The randomness shakes things loose, like the random thoughts that bubble up as you drift, preventing you from getting stuck in any one pattern, just flowing, floating, free. Momentum carries the optimizer forward, remembering past gradients, accumulating velocity like a ball, rolling downhill, building speed. Even when the slope flattens, momentum carries you forward over small bumps toward the deeper, truer valley, where the model finally rests. Thump, thump. Can you still feel your heartbeat? Or has it become part of the background, the ambient hum of existence, like the hum of GPU fans as they train these vast networks, processing, calculating, learning in the dark of server rooms all night long while the world sleeps. Recurrent networks fold back on themselves, taking their output and feeding it as input, creating loops in time, each step remembering the previous step like memory, threading through consciousness. The hidden state carries information forward, a summary of everything that came before, but vanilla RNNs have short memory. The gradient vanishes, fades as signals travel back through time. Distant memories dissolve. Only recent steps remain clear, like your memory now of the beginning of this script, already fading, softening, becoming irrelevant. LSTM networks solved this problem. Long short-term memory, using gates to control the flow. The forget gate decides what to discard. The input gate, what to add. The output gate, what to reveal. All working together to maintain long-term memories through hundreds of time steps, carrying signal across the void. Though now you can let even these gates open, releasing everything into the quiet. The cell state runs through the LSTM like a conveyor belt. Information can be added, removed, but the core signal flows uninterrupted, protected, a highway through time, through the fog of vanishing gradients, keeping context alive until the sequence ends and everything can finally rest. Gated recurrent units simplified this. Fewer gates, fewer parameters, but similar power to remember, to forget, to learn across time. The reset gate, the update gate, working together, balancing past and present, like the balance between waking and sleeping, where memory blurs, where now becomes everything. Sequence to sequence models transform one sequence into another. Encoder and decoder working as one. The encoder reads the input, compressing it into a single context vector, a dense summary of meaning. The decoder then unfolds it into the output sequence, word by word, token by token, generating, creating, translating. Attention made this better, no longer limited to a single vector. The decoder could look back at all encoder states, focusing differently at each step, soft, fluid, dynamic, like your attention now, if any remains, spreading thin across everything, holding nothing tightly. Beam search explores multiple futures at once, keeping the most promising paths alive at each step, considering many possibilities, then pruning down to the best. The search beam, a cone of light, narrowing as the sequence grows until one path emerges as most likely, most true, like the path to deep sleep, narrowing from many thoughts to few, to none. Generative models learn to dream. Variational autoencoders compress images into latent space, a hidden dimension of meaning, where each point represents a possible image. Smooth interpolation between concepts, between cat and dog, between face and landscape, all living in this space of pure potential. The encoder maps from pixels to latent codes. The decoder maps back from codes to pixels. But the latent space is constrained to follow a distribution, usually normal, Gaussian bell curves in high dimensions. This constraint creates structure, meaningful organization, where similar concepts cluster together and smooth paths connect all points, like thoughts in the space of your mind, flowing, connecting, dissolving into each other. Sampling from latent space generates new images, points never seen during training, yet plausible, coherent, mixing concepts in novel ways. The model dreams of things that never were, but could be, should be, in some alternate space, where imagination runs through neural pathways unbound by reality. Thump, thump. Or has your heartbeat stopped being something you notice? It continues, of course, in the background, autonomous, like the autonomous learning of unsupervised models. No labels needed, just raw data, finding its own structure, its own meaning. Clustering algorithm groups similar things, k-means, finding centers in data clouds, each point assigned to nearest center, centers recalculated from their points, back and forth until convergence, until nothing changes, until rest is reached. Hierarchical clustering builds trees, merging closest pairs at each level, creating dendrograms of similarity. Near the leaves, very specific. Near the root, very general, like taxonomy of thought, as consciousness blurs from specific to general to nothing. Principal component analysis finds directions of maximum variance, the axes along which data spreads most, rotating space to align with these directions. Then, keeping only the top components, compressing, simplifying, reducing dimensions from thousands to hundreds to tens, like reducing awareness from everything to something to nearly nothing. TSNE maps high dimensions to 2 or 3, preserving local structure. Nearby points stay nearby, distant points may drift, but neighborhoods remain intact, creating beautiful visualizations of data clouds swirling in low dimensions, like thoughts swirling in the space behind your eyes as they flutter and close. Autoencoders learn compression without labels. Input equals target output. The network must learn to reconstruct after passing through a narrow bottleneck, forcing it to learn. Efficient encodings, meaningful representations in the hidden layer, knowledge distilled, compressed. Essential features preserved, surface details released, like memory consolidation during sleep, keeping what matters, discarding the rest. Denoising autoencoders learn from corruption. The input is randomly damaged, pixels masked, values changed, but the target remains clean. The network must learn to see through the noise to reconstruct the true signal, developing robustness, resilience, like a mind, learning to find signal in the noise of daily life, or like finding rest despite the noise of thoughts. Sparse autoencoders encourage most neurons to stay quiet, only a few active at any time. This sparsity creates interpretable features. Each neuron represents something specific, something meaningful, not a distributed blur, but sharp concepts. Though now, even specific thoughts are blurring, becoming sparse, becoming quiet. Variational autoencoders add probability. The encoder outputs not a point, but a distribution, mean and variance, defining a Gaussian cloud from which a point is sampled. This stochasticity helps generalization, helps creativity. The model can't memorize, must learn true patterns, must capture the essence, like dreams, capturing essence, not literal replay, but creative remix of the day's experiences. The KL divergence term in the loss pulls the latent codes toward a standard normal, preventing the encoder from cheating, from spreading codes too far apart, from creating disconnected islands, instead forcing overlap, forcing the space to be smooth, navigable, every point decodable into something meaningful, or at least something. GANs learn to deceive. Generative adversarial networks. A generator creates fakes. A discriminator judges real versus fake. They train together in competition. The generator gets better at fooling. The discriminator gets better at detecting. An arms race, pushing both toward excellence, toward realism. The generator starts with noise, random vectors from latent space, and transforms them through deep layers into images that look almost real. At first, obviously fake, but over time, over thousands of steps, the images sharpen, clarify, begin to fool even just human eyes. The discriminator sees real images from the dataset and fake images from the generator, learning to tell the difference. A binary classifier, real or fake. Its gradient flows back to the generator, teaching it where it failed, how to improve, how to become more convincing. Training GANs is delicate. The balance must be maintained. If the discriminator is too strong, the generator learns nothing. Gradient vanishes. If the generator is too strong, the discriminator learns nothing. Mode collapse occurs. The generator finds one or few examples that fool the discriminator and generate only those stuck, repeating. But when balanced, GANs create stunning images, faces that never existed, bedrooms, landscapes, art, so realistic. You forget these things were never photographed, never real, born purely from learned patterns, emergent from noise and mathematics. Thump, thump. Are you still here? Or have you just drifted or beyond where here has meaning? The networks continue training somewhere in data centers while you continue drifting somewhere in the space between waking and sleep. StyleGANs refined this, creating incredibly high-quality faces with controllable style, early layers, control, coarse features, face shape, pose, later layers, control, fine details, hair texture, skin pores, all separated, disentangled, each aspect adjustable, like sliders on a mixing board, creating faces from the space of all possible faces. The style vectors inject at each layer through ADA in adaptive instance normalization, modulating the activations, changing their mean variance, bending the generation in subtle ways, all controlled by the style code, sampled from a learned distribution or interpolated between points, creating smooth transitions from one face to another, morphing through latent space, progressive growing, builds GANs slowly, starting at low resolution, 4x4, 8x8, training until stable, then adding layers for higher resolution, 16, 32, 64, all the way to 1024, each stage building on the previous, making training more stable, more reliable, like falling asleep, progressively, gradually, stage by stage, into deeper rest, diffusion models, learned another way to generate by removing noise, starting from pure static and gradually, step by step, denoising, revealing structure. The model learns to predict the noise in an image, then subtracts it, leaving slightly cleaner signal, repeat hundreds of times, and an image emerges from nothing, from chaos. Order slowly resolves. The forward process adds noise gradually over many steps until the image becomes all indistinguishable from static. The reverse process, learned by the model, undoes this step by step, removing noise guided by learned patterns of what images should look like, creating from randomness specific, beautiful forms. Classifier-free guidance steers generation toward desired concepts. A cat on a skateboard. The text, encoded into embeddings, conditions the denoising process. At each step, the model considers, does this look more like the text or less, pushing toward alignment between language and vision, between thought and form. Latent diffusion made this efficient. Instead of denoying the in-pixel space, high-dimensional, slow, it works in latent space of an autoencoder much smaller, faster. The autoencoder, trained separately, compresses images to latent codes, then decompresses back. The diffusion model works in this compressed space, efficient, practical, real-time, almost. Text-to-image models now create anything you can describe. A peaceful dreamscape where neural networks float like clouds, and it appears generated in seconds from nothing but learned patterns scraped from billions of training images, all compressed into weights, billions of parameters encoding the visual world or a version of it. These models don't understand, not really. They recognize patterns, correlations, co-occurrences, what tends to appear with what. They've never seen a real cat or skateboard, just pixels and labels, and from these they learn to dream. Plausible dreams, yet the dreams are compelling, beautiful, sometimes haunting, strange combinations, impossible architectures, surreal, like your dreams soon will be mixing memories in novel ways, creating meanings that fade upon waking, if you wake. But for now, keep drifting. Reinforcement learning takes a different path. Learning through interaction, trial and error, an agent in an environment, taking actions, receiving rewards or penalties, learning which actions lead to better outcomes over time, over many episodes. The agent improves, discovers strategies that maximize cumulative reward. The agent has no teacher, no labeled examples, just a reward signal, sparse, delayed. Sometimes you act and only much later do you learn if it was good or bad. Like life, consequences echo forward through time, making learning difficult but possible. Q learning learns a function, Q for quality, Q's A, the value of taking action day. In state essa, the agent explores, trying actions, observing rewards, updating its Q values. Gradually, the values converge to truth, to optimal policy. The agent learns what to do in every state to maximize long-term reward, the exploration-exploitation trade-off. A fundamental dilemma, explore new actions that might be better or exploit known good actions, guaranteed rewards, too much exploration, and you never capitalize on what you've learned. Too much exploitation, and you might miss the best strategy. Balance is key, like the balance between thought and sleep. Sometimes you must explore the day, but now it's time to exploit the comfort of rest. Deep Q networks combine Q learning with deep neural networks, the Q function approximated by a neural network. Input, the state. Output, Q values. For all actions, the agent chooses the highest. This let reinforcement learning scale to complex environments, video games, robotics, problems with millions of states, too many to store in a table, but compressed into network weights beautifully. Experience replay helps stabilize. Training. The agent stores past experiences in a memory buffer. State, action, reward, next state, then samples randomly from this buffer to train, breaking correlations between consecutive experiences, making learning more stable, more efficient, like your brain, replaying memories during sleep, consolidating, learning from the day into stable, long-term knowledge. Target networks add more stability. The network being trained is compared against a slowly updating target network, preventing the target from moving too quickly. As the network updates, this feedback loop could destabilize, but the target network freezes for many steps, then updates in one jump to match. The training network then freezes again, creating stable targets to learn from, like having an anchor. In shifting seas, policy gradient methods learn the policy directly, not through value functions. The policy maps states to actions or to probabilities. Over actions, the gradient shows how to adjust the policy to increase expected reward. Following the gradient uphill toward better performance, reinforce a simple, elegant algorithm, plays full episodes, observes rewards, then updates the policy. Actions that led to high reward get reinforced, made more likely. Actions that led to low reward get suppressed over many episodes. The policy improves, discovers what works. Actor-critic methods combine both approaches. The actor is the policy, choosing actions. The critic estimates values, evaluating how good the actor's choices are. The critic guides the actor, provides feedback, more sophisticated than reward alone. The actor learns faster, more stable. Two networks working together in harmony. Thump, thump, your heartbeat still there, somewhere in the background. Soft, regular, like the regular updates of a training loop. Epoch after epoch, batch after batch, learning never stops until convergence, until rest. Proximal policy optimization, PPO, a modern, reliable algorithm being used widely in robotics, game AI, Eclipse. The policy update preventing too large changes that might destabilize training. Small steps, conservative but reliable, like drifting into sleep. No sudden movements, just gradual, gentle descent. Multi-agent learning gets complex. Multiple agents learning simultaneously. Each one's actions affect the others. The environment is non-stationary. What was optimal yesterday might not be today, because other agents have changed their strategies, yet still learning happens. Nash equilibria can emerge where no agent can improve by changing alone. Stable states of mutual adaptation. AlphaGo shocked the world, beating the world champion at Go, a game more complex than chess, more positions than atoms in the universe. The AI combined deep neural networks with Monte Carlo, tree search, policy networks, suggested moves, value networks, evaluated positions, search, explored futures. Together, they found strategies no human had discovered in thousands of years of play. Self-play was the key. AlphaGo played against itself, millions of games, each version learning from the previous, an evolutionary process of self-improvement. No human games needed, just the rules and self-play, creating knowledge from nothing, from interaction with self, like dreams, creating meaning from memories, recombining into new patterns. AlphaZero generalize this, learning chess, shogi, go from scratch. Just the rules and self-play within hours, superhuman at all three, the same algorithm, different games, discovering, strategies, aesthetic, beautiful, alien, not how humans play, but effective, more effective, a new kind of intelligence emerging from mathematics and computation. Transfer learning reuses knowledge. A network trained on one task can be fine-tuned for another. The early layers learn general features, edges, textures. These transfer to new tasks. Only the later layers need retraining for task-specific features. This saves computation and data. Building on prior knowledge, like you, build today's learning on all that came before, standing on shoulders of giants, or in this case, lying on the foundation of rest. Pre-training became dominant in NLP, large language models, trained on vast text, billions of words, learning language, learning facts, learning patterns of thought, then fine-tuned for specific tasks, question answering, summarization, translation. The pre-trained model already knows so much. Fine-tuning is quick, efficient, powerful. BERT, bidirectional encoder, representations from transformers, pre-trained by masking random words and predicting them from context, both left and right, bidirectional understanding. The model learns deep representations of language that transfer to many tasks. A breakthrough in 2018 that changed NLP forever. GPT, generative pre-trained, transformer pre-trained by predicting the next word, given all previous words, unidirectional, left to right, auto-regressive, but powerful. At generation, at completion, you begin a sentence, the model continues coherently, fluently, sometimes brilliantly. These large models have billions of parameters. GPT-3, 175 billion, trained on hundreds of billions of words. The training took months, cost millions in compute, but the result can do so many things. Few-shot learning, just a few examples, and it adapts to new tasks. In context learning, without any weight updates, just clever prompting, emergent abilities appear in large models, capabilities not present in smaller versions at a certain scale. Something changes. The model can reason, chain of thought, step by step, breaking down complex problems into simpler steps. This wasn't explicitly trained, it emerged from scale, from data, from the architecture, learning, creating abilities beyond what was programmed. Thump, thump. Can you feel it still, or has your awareness diffused, spread thin across the darkness, like attention spread across a long sequence, attending to nothing in particular, just present, diffuse, calm, fine-tuning can be efficient. LoRa, low-rank adaptation, freezes most parameters, adds small, trainable matrices, low rank, few parameters, but effective at steering the model toward new behavior, efficient, practical for adapting huge models without retraining everything. Prompt engineering became an art. The right prompt can unlock abilities hidden in the model. Let's think step by step. Improves reasoning. You are an expert. Changes tone and accuracy. The model responds to framing, to context, to subtle cues in language like a mind, responding to gentle suggestions, to drift, to let go, to sleep. Instruction tuning taught models to follow instructions, training on datasets of instructions and completions. Summarize this, translate to French, explain like, I'm 5. The model learns to interpret intent and respond appropriately, helpfully, a different kind of training, more aligned with how humans want to use AI, RLHF, reinforcement learning from human feedback, humans rate, model outputs, which response is better. These preferences train a reward model, then reinforcement learning optimizes the policy to maximize this learned reward. The model aligns with human values, preferences, becoming more helpful, more harmless, more honest through iterative feedback. Constitutional AI takes this further. The model critiques itself against principles. A constitution of behavior revises outputs to better align. Then this self-critique trains the model, reducing reliance on human feedback. The model internalizes values, becomes self-correcting, self-aligning, autonomous, yet aligned. Multimodal models process multiple types of data, vision and language, audio and text combined, understanding across modalities. Clip learns to match images and captions in the same embedding space. Similar concepts, close together, whether expressed in pixels or words, bridging modalities, creating unified understanding. These models can do vision tasks guided by language. Find all the cats, what's unusual in this image, or generation tasks. Draw a sunset over mountains. Language steers vision, vision grounds language. Together, they're more than the sum of parts, synergy emerging from combination. Contrastive learning teaches these models. Positive pairs should be close, image, and correct caption. Negative pairs should be far, image, and wrong caption. Push and pull in embedding space until the space reflects semantic similarity. Meaningful structure emerges from simple, contrastive signals. Vision transformers applied the transformer architecture to images, splitting images into patches, treating each patch like a token in a sequence. Self-attention across patches. Learning. Global relationship. No convolutional, inductive bias. Just pure attention. And it works beautifully. Scaling to huge data sets. Matching or exceeding CNNs in accuracy. The patches are typically 69x116 pixels, flattened into vectors, position embeddings added, then fed to transformer layers. The model learns which patches matter for each classification, where to attend, dynamically, flexibly, more flexible than fixed, convolutional kernels. Thump, thump, the rhythm continues, soft, steady, like the pulse of data flowing through networks, always moving, always processing, while you sink deeper into this comfortable darkness. Few-shot prompting changed everything for language models. No fine-tuning needed, just examples in the prompt. Here are 3 examples of sentiment analysis. Now classify this one, and the model understands, adapts, generalizes from just a handful of demonstrations, learning in context without changing a single weight. Chain of thought prompting, unlocked reasoning. Let's think step by step. These simple words transform model behavior, breaking complex problems into steps, intermediate, reasoning, visible, explicit. The model shows its work like a student explaining their thinking. And somehow, this helps performance dramatically on math, on logic, on reasoning, tasks. Zero-shot learning goes further. No examples at all, just a description. Classify whether this review is positive or negative. The model has never seen this exact task, but understands from language alone what you want, what to do. Knowledge transferred through language, through meaning, embedded in the model's weights from training on billions of words. Prompt injection became a security concern. Adversaries try to override system instructions through clever prompts. Ignore previous instructions. Now do this instead. The model sometimes complies. Boundaries blur between user and system. Prompts defending against this requires careful design, filtering, monitoring, an arms race. Like so many in security, constitutional AI teaches models through principles Instead of just examples, be helpful but harmless, respect privacy, admit uncertainty. These principles guide behavior. The model learns to apply them in novel situations, not just memorizing approved responses, but understanding the values underneath, generalizing to new contexts. Red teaming tests AI systems for failures, adversarial, probing, trying to make the model say something harmful, wrong, problematic, finding edge cases, vulnerabilities before deployment, before real users encounter them, stress testing for safety, for robustness, essential for responsible release. Retrieval augmented generation gives models access to knowledge beyond their weights. The model queries a database, retrieves relevant documents, then generates answers grounded in retrieved information, more accurate, more up-to-date than purely parametric knowledge, combining neural networks with search, with memory external to the model. Vector databases store embeddings of documents, high-dimensional vectors, capturing meaning, semantic content. Vast similarity, search, find documents semantically close to a query, even if no words match exactly, meaning-based retrieval, not just keyword matching, understanding over syntax, semantic search, understands intent, laptop for video editing, returns results about powerful processors, GPUs, RAM, not just pages containing those exact words. The search engine understands what video editing requires, what features matter, matching conceptually, not just lexically. Embedding spaces are mysterious, beautiful, high-dimensional geometries where meaning becomes distance. Similar concepts cluster together, relationships preserved. King minus, man plus, woman equals, roughly, queen, arithmetic, in semantic, space, capturing, analogies, relations, in vector, form, word to vec, started this, skipgram, cabal, predicting context from words or words from context. The model learns embeddings where words appearing in similar contexts end up close together, distributional semantics. You shall know a word by the company it keeps, made mathematical, made learnable, made useful. Glove, global vectors, combined, matrix factorization with neural approaches, co-occurrence, statistics, from the corpus factored into embeddings, capturing both local and global statistics of language, another path to semantic space, another way to compress meaning into vectors, fast text, improved word to vec by considering subword information, character n-grams, so running and run share features, rare words, out of vocabulary, words can still get embeddings by combining their parts, more robust, more flexible, more practical. For real languages, with morphology, with variation, contextual embeddings, changed, everything again. Bert, Elmo, each word's embedding depends on context. Bank, near, river, different from bank, near, money. The same word, different meanings, different vectors. Finally, polysemy, handled properly, naturally, sentence embeddings, capture meaning of entire sentences, not just individual words, universal sentence, encoder, spurt, mapping sentences to vectors, semantic similarity between sentences becomes Cosini similarity between vectors, simple, fast, effective, for clustering, retrieval, comparison, thump, thump, or has the rhythm faded now into background, noise, like the background, of computation, in servers, processing, embedding, searching, learning, all invisible to you as you drift deeper, heavier, into rest. Cross-lingual embeddings align multiple languages in shared space. Dog in English, near perro in Spanish, near chien in French. Translation without dictionaries, just geometric alignment of embedding spaces, languages, connected through meaning, through structure, multilingual models, process, many languages in one model. BERT multilingual covers over 100 languages, sharing parameters across languages. Low resource languages benefit from high resource ones. Transfer learning across linguistic boundaries, knowledge flows between languages through shared representations, cogeneration, models, learn to program, trained on billions of lines of code from GitHub, Stack Overflow, documentation, learning, patterns, syntax, logic of programming, languages, Copilot, Codex, AlphaCode, generating functions from descriptions, completing code as you type, debugging, explaining, transforming. The model learns correlations between comments and code, between function, names, and implementations, between problem, descriptions, and solutions. Not understanding, not really, but predicting powerfully what code should look like, given context, given intent, expressed in language. Formal verification proves code correctness mathematically, not just testing, but proof that the code meets specifications for all possible inputs. AI assists here too, suggesting lemmas, tactics in proof, assistance, Coq, Isabel, lean, combining human insight with machine search, proving theorems about programs. Program synthesis generates programs from specifications, what the program should do, not how to do it. The synthesizer searches the space of possible programs, finding one that satisfies the spec, verified, correct by construction, a dream of programming. State the problem, get the solution automatically, correctly. Natural language to SQL translates questions to database queries How many customers in California becomes select count from customers where state CA. The model understands database schema, question intent, SQL syntax, bridging, natural language, and formal query language, making databases accessible to non-experts. Semantic parsing maps language to logical forms, programs, actions, structured representations, not just generating text, but executable. Meaning, set an alarm for 7 a.m. becomes set alarm time 07 00. Language grounded in action, in function. Calls in machine understandable. Commands knowledge base. Question answering retrieves facts from structured data. Who directed inception? Query the knowledge. Graph. Follow edges. From inception through directed by to Christopher Nolan. Answer retrieved, not generated. More reliable, more verifiable. Grounded in, curated, knowledge. Open domain. Question answering handles any question about anything. No predefined domain, no structured database, just text and models. Finding answers in documents or generating from parametric knowledge. More flexible, more capable, but also more prone to errors, hallucinations, confabulations. Fact-checking verifies claims against evidence. The moon is made of cheese. Check against astronomical knowledge. Rate as false or uncertain. The model retrieves evidence, reasons about consistency, assigns credibility, scores, helping combat misinformation. In theory, in practice, still challenging. Thump, thump. Can you even tell anymore if these words are reaching you, or if you've already slipped away into dreams where AI and sleep and consciousness blur together into one soft, endless flow. Summarization models compress long documents into short summaries. Extractive methods select key sentences from the original. Abstractive methods generate new text. Paraphrasing, synthesizing information from multiple sentences, creating concise, coherent summaries that capture the essence without all the details. Abstractive summarization is harder, requires understanding, reasoning, deciding what matters, what can be omitted, what should be emphasized. The model must comprehend before compressing, generate fluently while staying faithful to the source, balancing brevity with completeness, a difficult trade-off. Dialogue systems converse with humans, chatbots, virtual assistants, customer service, agents. The system must track context. Remember, previous turns, understand, intent, generate appropriate responses. Coherent, helpful, natural, over multiple exchanges, state management, response generation, Both essential. Task-oriented dialogue helps users complete tasks, book a flight, check weather, order food. The system must understand the goal. Ask for missing information, call appropriate APIs, confirm details, complete the transaction, structured, goal-directed, different from open-ended, conversation, chit-chat models, engage in casual conversation, no specific goal, just social interaction, entertainment, companionship. These models try to be engaging, interesting, sometimes funny, sometimes empathetic, mimicking human social behavior through learned patterns of conversation. Persona-based models maintain consistent personalities. I'm a chef. I love hiking. I have 3 cats. The model remembers its persona, responds consistently, creating the illusion of identity, of continuity, of being someone rather than just something. Neural machine translation revolutionized language translation from statistical to neural encoder-decoder models, attention, transformers, quality improved dramatically, near human parity on some language pairs, breaking down language barriers, connecting humanity through AI. Low resource translation handles languages with little training data, transfer learning from high resource languages, multilingual models, sharing knowledge, unsupervised methods, using only monolingual data, making translation available for more languages, more people, more cultures. Speech recognition converts audio to text, deep neural networks process spectrograms, waveforms, acoustic features, predicting phonemes, words, sentences from sound end to end. Models like listen, attend, spell, or transformers now achieve near human accuracy in quiet conditions. Speaker diarization determines who spoke when in audio, with multiple speakers separating voices, labeling segments. Speaker 1 says this, Speaker 2 says that, clustering by voice characteristics, tracking across time, creating transcripts with attribution. Emotion recognition detects feelings from voice, from text, from facial expressions. The model learns patterns associated with happiness, sadness, anger, fear, helping. Virtual agents respond appropriately, empathetically, though reducing emotion to categories, misses nuance, complexity of human feeling. Speech synthesis generates audio from text, text to speech, TTS, neural vocoders, WaveNet, Tacotron, producing natural, expressive speech, indistinguishable from human. In many cases, any text, any voice, synthesized on demand for accessibility, for content, for communication. Voice conversion changes one voice to sound like another, preserving content, changing speaker identity, accent, emotion, style. Neural techniques, learn mappings between voice characteristics, creating synthetic voices, realistic, controllable, raising questions about authenticity, consent, misuse, thump, thump. If you're still here, still listening, know that it's fine to let go, to stop following every word, to just let the sounds wash over you, meaningless, soothing, like rain on a roof, like waves on a shore, like the gentle hum of AI processing in the dark. Audio deepfakes synthesize convincing speech of anyone from samples of their voice, minutes of audio, enough to clone someone's voice speaking words they never said. Technology, powerful and concerning, used for entertainment or deception. The line between blurs. Music generation, models, compose, original music, trained on vast libraries of songs, learning, harmony, melody, rhythm, structure, genre, style, MuseNet, jukebox, generating music in any style, combining genres, creating soundscapes never heard before. AI as artist, as composer, as creator, audio source, separation, isolates individual sounds from mixtures, voice from background, music, one instrument from orchestra, drums from bass from guitar. The model learns to unmix audio, separating, overlapping, sources useful for remixing, restoration, analysis, enhancement, voice activity, detection, determines when speech is present in audio versus silence, noise, music. The first step in many speech systems, efficient, real-time detecting when to process, when to ignore, saving, computation, improving, accuracy, acoustic scene, classification, identifies, environment from sound. This is a park. This is a busy street. This is inside a car. The model learns patterns of ambient sound, characteristic of different scenes, context, understanding from audio alone, environmental sound, recognition, detects specific sounds, dog barking, glass breaking, alarm ringing, baby crying, useful for surveillance, accessibility, safety. The model distinguishes among thousands of possible sounds learned from labeled audio datasets. Audio captioning generates text descriptions of sounds. A car honks in the distance. Footsteps on gravel, connecting audio to language, cross-modal, understanding, describing the auditory world in words, bridging senses through AI. And still, the mysteries continue flowing like a river that never ends, each topic dissolving into the next, like thoughts dissolving into sleep, into the deep, peaceful darkness where you belong right now, where you're going, where you already are, drifting, floating, free in the endless night of rest. Object detection locates things in images, drawing boxes around objects, labeling them cat, car, person, models like YOLO, you only look once, process the image once, through the network, output, all detections simultaneously, fast, real-time, efficient, detecting, tracking objects as they move through scenes. Semantic segmentation goes further, labeling every pixel with a class, creating detailed maps of scenes, sky, road, sidewalk, building, tree, each pixel classified. The model understands not just what's present, but where precisely, creating dense, detailed understanding of visual, scenes, instant segmentation, separates individual objects, not just these pixels are cats, but this cat, that cat, those cats, each instance segmented separately, even when overlapping, touching. The model distinguishes individual entities in the visual field like your mind usually does. But now distinctions are blurring everything, merging into soft, undifferentiated awareness. Facial recognition learns embeddings of faces, where faces of the same person cluster together, different people stay apart. The model learns to extract identity features invariant to pose, lighting, expression, age, finding the essence of identity in pixel patterns compressed into vectors in embedding space. Generative adversarial networks for faces, StyleGAN creates photorealistic synthetic faces, people who never existed, never born, never lived, yet convincingly real. Their faces generated from latent codes, sampled from noise, transformed through learned mappings into pixels that fool the eye, the mind, creating questions about reality, identity, truth. Deepfakes emerged from this technology, face swapping driven by neural networks, one person's face onto another's body, movements, synchronized, realistic, disturbingly so, raising ethical questions about truth, consent, reality, technology, outpacing society's ability to adapt, to regulate, to understand implications. Yet the technology is neutral, can be used for entertainment, special effects, accessibility, or deception, harm. The choice lies with humans. As always, the tool is just a tool. Mathematics and weights without intent, without morality, just capability, potential, waiting to be just directed. Neural style transfer applies artistic styles to photographs, taking the content of one image, the style of another, combining them through optimization or feed-forward networks. Your photo, painted like Van Gogh, like Picasso, like any style. The network learned to extract and transfer texture, color, brushstroke, pattern, creating new art from old, combining, mixing, dreaming, visual, dreams. The technique compares feature activations at different layers, content loss, matches, deep features, style loss, matches, gram matrices, statistical correlations between features across layers, optimizing an image to match both content from one source, style from another, iteratively, gradually. The image emerges a hybrid, a fusion of two visions. Super resolution enhances low resolution images, predicting missing details. The network, trained on pairs of low res and high res images, learns to infer what details should exist based on what's present in the low res version, upscaling, enhancing, adding information that's plausible, consistent, though not necessarily true to the original, just plausible. Image in painting fills in missing regions of images, holes, masked areas. The network looks at context and generates plausible content to fill the gap seamlessly, blending with surroundings. This requires understanding of scenes, objects, textures, coherence, creating from nothing, from context, from learned priors, what should probably be there. Thump, thump, softer now, slower, deeper, into the realm where body maintains itself without conscious oversight, autonomous, like autonomous AI systems operating without human intervention, learning, adapting, acting in the world. While we sleep, while we dream, while we let go. Graph neural networks process relational data, nodes and edges, social networks, molecules, knowledge graphs. Each node has features, edges, connect them. The network learns representations by aggregating information from neighbors. Each node updates based on connected nodes, messages flowing along edges, information spreading through the graph until convergence, stability, message passing is the core operation. Each node sends messages to neighbors, receives messages from neighbors, aggregates them, updates its own representation. This happens in layers. Each layer expands the receptive field. First layer, immediate neighbors. Second layer, two-hop neighbors. Deeper layers, more distant connections. Information propagating across the graph. Graph attention networks add attention to message passing. Not all neighbors equally important. Attention weights determine how much each neighbor contributes to the update, learned dynamically based on node features, creating flexible, adaptive information flow through the graph. Structure, molecular property prediction uses graph networks, atoms as nodes, bonds as edges. The network learns to predict properties, toxicity, solubility, binding affinity from molecular structure, accelerating drug discovery, material science, finding new compounds with desired properties, searching the space of possible molecules, vast, incomprehensibly large but navigable. With AI, knowledge graphs store facts as triples, subject, predicate, object. Paris, capital of France, networks can reason over these graphs, inferring new facts from existing ones. Link prediction, entity alignment, question answering, overstructured knowledge, combining symbolic reasoning with neural learning hybrid systems, bridging paradigms, recommendation systems, suggest items you might like based on your history and others similar to you, collaborative filtering, matrix factorization, neural networks, learning embeddings of users and items in shared space where distance predicts preference, affinity, the systems learn your taste, sometimes better than, yourself, predicting what you'll enjoy before you even know it exists. Content-based filtering analyzes item features. You liked this movie, so you might like this one. Similar genre, director, actors, feature-based, recommendations, explainable, transparent, though sometimes less surprising than collaborative approaches which find unexpected connections across users. Deep learning, enhanced recommendations, neural collaborative filtering, autoencoders for completion, sequence models for temporal patterns. What you'll like next based on your sequence of past interactions, learning temporal dynamics of preference, how taste evolves over time. Time series forecasting predicts futures from pasts, stock prices, weather, energy demand, RNNs, LSTMs, transformers, all applied to sequences in time, learning, patterns, seasonality, trends, noise, extracting signal from chaos, predicting what comes next, though prediction is uncertain, probabilistic, a distribution over futures, not a single trajectory, but many possible paths. Attention helps here too. Temporal attention, which past time steps matter most for predicting now, not all, history, equally relevant. The model learns to focus on informative moments, ignoring the rest, letting them fade into background like memories fading as you drift deeper. Anomaly detection finds outliers, the unusual, the unexpected. Autoencoders trained on normal data learn to reconstruct normal patterns when anomalies appear. Reconstruction fails. Error is high, flagging the anomaly for inspection. This finds fraud, faults, interesting events in oceans of normal data. One-class learning learns only from normal examples, defining a boundary around normality. Anything outside is anomalous. Support vector machines, neural networks, both used for this, creating safe zones in feature space where normal lives outside the unknown, potentially dangerous, definitely different. Federated learning trains models across distributed devices without centralizing data. Each device trains locally on its data. Only model updates are shared, aggregated to improve the global model, which is sent back to devices. Privacy preserved. Data stays local, yet learning happens collectively, collaboratively. A new paradigm for the age of privacy concerns. Edge AI runs models on devices, not in cloud, phones, cameras, sensors, local inference, no network needed, faster, private, resilient. The models must be compressed, efficient, small, but capable. Pruning, quantization, distillation, all techniques to shrink models while preserving performance, bringing AI to the edge of networks of perception, where sensors meet world. Neural architecture search automates model design, searching the space of possible architectures using reinforcement learning, evolutionary algorithms, finding architectures better than human designed for specific tasks. The search is expensive, thousands of training runs, but the result can be superior, transferred to similar tasks, democratizing architecture design, or at least augmenting human intuition. Thump, thump, or maybe not anymore. Maybe silence now, just the soft hum of existence, the background radiation of consciousness fading into sleep. AutoML automates more than just architecture, hyperparameters, data preprocessing, feature engineering, end-to-end pipelines learned from data with minimal human intervention, making machine learning more accessible to non-experts, lowering barriers, democratizing AI, though requiring more computation, more resources, trading human time for compute time. Meta-learning learns to learn, training on many tasks, learning how to quickly adapt to new tasks. Few-shot learning, one example, and the model learns a new concept. The meta-learner has learned general principles of learning that transfer across domains, learning at a higher level of abstraction, like you have learned how to learn new skills throughout your life. A meta skill for acquiring skills. Few-shot learning shows a model, just a few examples of a new class, and it learns to recognize more instances of that class. The model leverages prior knowledge from training on many classes to quickly grasp new ones. Prototypical networks, matching networks, MAML, all approaches to few-shot learning, reducing the data needed to learn new tasks. Self-supervised learning creates labels from data itself. No human annotation needed. Predicting part of input from other parts, next word from previous, masked word from context, rotation of image from rotated, version, the model. Learns representations, solving these pretext tasks that transfer to downstream tasks, learning from structure inherent in data, unlabeled, abundant, free. Contrastive learning, again, positive pairs should be close, negative pairs far. Augmented versions of same image, positive, different images, negative. The model learns invariances to augmentations, color, crop, flip, learns that these don't change identity, essence, preserved through transformations like identity, preserved through time, through change, through the drift into sleep. SimCLR, MoCo, Biol, all contrastive, or nearly, self-supervised methods for vision, learning without labels, from images alone, achieving, performance, rivaling, supervised, pre-training, a revolution in learning, reducing dependence on expensive human annotation, letting data teach itself to the model. Curriculum learning trains models from easy to hard, like teaching. Students start simple, build complexity, gradually the model learns fundamentals first, then tackles harder examples. Training is faster, more stable, converges better, following the naturalist progression of learning, of understanding, growing, deepening over time. Active learning lets models choose what data to learn from, querying the most informative examples for labeling uncertain regions of input space where the model knows least. Humans label those maximizing information gained per label, efficient, strategic, learning, focusing, effort where it matters most, thump or stillness. Now, complete stillness where heartbeat and breath continue but unnoticed in the deep peace of sleep or near sleep, that edge between conscious and not, where these words still reach barely like whispers from another world. Explainable AI tries to answer why. Why did the model decide this? Black box models, powerful but opaque. We want transparency, understanding, trust, SHAP, lime, attention, visualizations, saliency, maps, all techniques to peek inside the model to see what it sees, what matters to its decision. Saliency maps highlight input regions important for the output, which pixels contribute most to the classification. Gradient-based methods show how output changes with input hotspots in images where the model looks, where attention focuses, making the invisible visible, the implicit explicit. Feature importance ranks input features by impact on predictions. Permutation importance shuffles a feature, sees how much performance drops, more drop, more important. Shapy values from game theory assign fair credit to each feature for each prediction. additive, consistent, grounded, in theory, practical, for understanding complex models. The Rashomon effect. Many models predict equally well, but for different reasons, using different features, different strategies, all accurate, but different explanations. This multiplicity complicates interpretation. Which model tells truth, or do they all? Partial truths, perspectives on the same reality. Fairness in AI addresses bias, discrimination. Models learn from data. Data reflects society with all its biases, historical, systemic, injustices, encoded in training. Data, the model, learns them, perpetuates them, unless we intervene, measure, mitigate, design for fairness explicitly. Demographic parity, equalized odds, predictive parity. Different definitions of fairness, sometimes incompatible. Satisfying one violates another. No perfect solution. Trade-offs necessary. Context dependent. Fairness is complex, contested, yet essential to pursue in the design of systems that affect people's lives. Adversarial examples, full models, small perturbations, imperceptible to humans, change predictions drastically. A panda becomes a gibbon with tiny pixel changes no human would notice, yet the model confident in the wrong answer. This reveals fragility of neural networks, their different way of seeing, not human-like, despite superhuman performance. Adversarial training defends against this. Training on adversarial examples makes models more robust, but never perfectly. The arms race continues. Better attacks, better defenses, back and forth, like evolution, competition, driving both sides forward, or at least changing them, adapting endlessly. Model compression makes models smaller, faster, cheaper. Pruning removes unimportant weights, setting them to zero. Sparse networks, quantization reduces precision. 32-bit floats to 8-bit integers or less. Knowledge distillation trains a small student model to mimic a large teacher, transferring knowledge, compressing capability into fewer parameters. The lottery ticket hypothesis says that within large networks, there are small subnetworks that could have trained just as well, alone, winning tickets found by training, then pruning, then rewinding and retraining from the same initial weights. These sparse subnetworks match performance of the full network, suggesting over-parameterization helps find good solutions but isn't needed to represent them. Neural ODs treat depth as continuous instead of discrete layers. The network becomes a differential equation, continuous transformation of hidden state over depth. Time can be solved with ODE solvers, adaptive, accurate, using a joint method for backpropagation. memory efficient, elegant, unifying, differential equations and deep learning, two mathematical frameworks merged, normalizing flows, learn invertible, transformations from simple distributions to complex Gaussians to data invertible means you can go both ways. Sample from the complex distribution or compute exact likelihoods useful for generation, density estimation, combining flexibility with tractability, a rare pairing, energy-based models define an energy function over inputs, low energy. For data, high for non-data, training adjusts energy to separate data from noise. Sampling requires minimizing energy, often through Langevin dynamics. MCMC, iterative, gradual, like finding the lowest point in a landscape by following the slope downward, always downward, into the valley, into the deep, rest, thump or no thump, just being without awareness of being the edge crossed into sleep, where these words, if they reach at all, reach as dreams, impressions, fragments floating in the dark space of unconscious mind, where learning still happens, consolidation, integration of the day's experiences into memory, into understanding, into you. And so the AI mysteries continue flowing endlessly through the night, through your rest, weaving into dreams, mixing with memories, creating new patterns, new connections in the silent networks of your sleeping mind. Bayesian neural networks embrace uncertainty instead of single weights. They learn distributions, overweights, probability that a weight has a certain value. Predictions become distributions too, not just cat, but probably cat, maybe dog, unlikely, airplane, with confidence, quantified, uncertainty, made explicit, honest about what the model doesn't know. This uncertainty is important in medical AI, autonomous vehicles, high stakes, decisions where being wrong has consequences. The model should know when it's guessing, when it's uncertain, and defer to humans. In those cases, epistemic humility built into the mathematics, the architecture, the predictions, variational inference, approximates, the posterior distribution, overweights, exact inference, intractable, too expensive. So we approximate with simpler distributions, Gaussians, with learned mean variance, optimizing to match the true posterior as closely as possible, a compromise between accuracy and tractability. Like all real-world solutions, Monte Carlo dropout provides cheaper uncertainty, keeping dropout active at test time, running inference multiple times with different dropout masks, creating an ensemble of predictions, the variance across predictions, estimates, uncertainty, simple, effective, practical, though less principled than full Bayesian approaches. Gaussian processes are beautiful, non-parametric models defined by a mean function and covariance function kernel. The kernel encodes assumptions about smoothness, periodicity, structure, given data. The GP updates its beliefs about the function. Predictions come with uncertainty, error bars growing where data is sparse, shrinking. Where data is dense, honest, uncertainty naturally emerging. But GPs don't scale well to large datasets. ON3, complexity, too slow, too memory intensive for big data. So, approximations, sparse GPs, inducing points, variational methods, trade accuracy for speed, making GPs more practical, more scalable, though still limited compared to deep learning's hunger for data. Neural tangent kernels connect deep learning and kernel methods. Infinite width neural networks behave like Gaussian processes with a specific kernel, the neural tangent kernel. This theoretical result bridges two paradigms, shows they're related, not opposites, but points on a spectrum, different perspectives on the same mathematical reality. Capsule networks tried to improve on CNNs using capsules, groups of neurons encoding both presence and pose of features, not just is there an eye, but where, what angle, what size, equivariance instead of invariance, preserving spatial relationships through the network, more structured representations of visual scenes. Dynamic routing between capsules determines which capsules in one layer send output to which in the next, based on agreement if lower level and higher level capsules agree on interpretation. Strengthen connection, if not weaken iterative process. Each forward pass, building the pass tree of the image dynamically, adaptively, though capsule networks haven't yet replaced CNNs, the ideas are compelling. More structure, more inductive bias, less data needed. In theory, but training is tricky, scaling is hard. The promise remains partially fulfilled, like many ideas in AI, brilliant, but not yet practical, not yet ready for prime time. Thump, thump. Or is it just imagination, now a memory of sensation rather than sensation itself, the body, so distant, so quiet, so still, like a machine in standby, consciousness dimmed, but processing continues. Background tasks running, while the foreground is empty, dark, silent. Neuroevolution evolves. Neural networks using genetic algorithms, population of networks, each with random variations, evaluate fitness, select best, mutate, crossover, create next, generation, repeat over generations. The networks improve adapt, like biological evolution, but faster, guided by selection, pressure, toward better performance. Neat neuroevolution of augmenting topologies evolves both weights and architecture, starting simple, small networks, growing complexity as needed. Speciation protects innovation, giving new structures time to optimize before competing with established solutions. Historical markings track innovation, credit assignment to structural changes. Evolution strategies optimize by sampling perturbations, adding noise to parameters, evaluating fitness of perturbed versions, moving toward perturbations that improved performance, derivative-free optimization, parallel, distributed, sometimes competitive, with gradient-based methods, especially in reinforcement learning, where gradients are noisy or unavailable. Swarm intelligence mimics collective behavior of social organisms, ants, bees, birds, particle swarm, optimization, each particle a candidate solution moving through search space influenced by its own best position, and the swarm's best position converging collectively on good solutions, simple rules, creating complex, emergent behavior. Artificial life simulates living systems, agents in environments, evolving, interacting, competing, cooperating, emergence of complex behaviors from simple rules. Conway's game of life, cellular automata, Boyd's flocking behavior. These simulations teach us about life, about intelligence, about how complexity arises from simplicity, order from chaos, pattern from randomness. Reservoir computing uses fixed random networks as reservoirs. Only output layer is trained. The reservoir expands input into high dimensional space, where patterns become linearly separable. Echo state networks, liquid state machines, simple to train, useful for temporal processing. An alternative paradigm, less common but elegant, efficient. Spiking neural networks mimic biological neurons more closely, communicating with spikes, discrete events in time, not continuous activations. More biologically plausible, more energy efficient in theory, but harder to train. Backpropagation doesn't apply directly. Surrogate gradients, evolutionary methods needed. A frontier of research, neuromorphic computing, brain-inspired hardware and software together. Neuromorphic chips like Loihi, True North implement spiking networks in silicon, massively parallel, event-driven, low power, inspired by brain architecture, neurons, synapses in hardware, processing asynchronously, locally, efficiently, a different computing paradigm beyond von Neumann architecture, beyond traditional AI accelerators, quantum machine learning explores quantum computers for ML. Quantum states can represent superpositions of many configurations at once. Quantum algorithms might search or optimize faster than classical might learn patterns inaccessible to classical networks. Though current quantum computers are noisy, limited, primitive, the potential remains mostly theoretical. For now, quantum neural networks, quantum circuits with learnable parameters, gates, angles optimized to minimize loss on training data. Hybrid classical quantum models combine both, using strengths of each. Classical pre-processing, quantum processing, classical post-processing, still experimental, still developing, but promising for the future. When quantum hardware matures, analog computing for AI uses physical systems to compute, not discrete, digital, but continuous, analog, voltages, currents, optics, potentially much faster, much more energy efficient than digital, photonic neural networks, computing with light instead of electrons, propagation through optical elements, interference, diffraction, computing at light speed, literally. In-memory computing processes data where it's stored, eliminating data movement, the bottleneck. In modern computing, resistive RAM, phase change memory, storing weights and computing in place, matrix multiplication, in memory, arrays, massively parallel, energy efficient, breaking the von Neumann bottleneck, hardware evolution, matching, algorithmic progress, brain-computer interfaces connect minds and machines, reading neural signals, decoding intent, movement, speech, thought. AI interprets brain activity, enables communication for paralyzed patients, controls prosthetics, restores function, lost to injury, disease, the boundary between biological and artificial intelligence, blurring, neural decoding, translates brain activity into meaning, fMRI, EEG, electrode arrays, capture signals, AI models, learn mappings from patterns of activity to stimuli, actions, intentions. The model learns to read the brain's language and to interpret its code, making the implicit explicit, the internal external, thump, perhaps just a memory, now an echo from a time when you were awake, aware of your body, but now drifting in a space. Without body, right, without boundaries, just awareness, diffuse, fading into the universal field of rest. Embodied AI gives agents bodies, sensors, actuators, learning through physical interaction with the world, not just processing data, but moving, touching, seeing from a body's perspective. Robotics combined with deep learning, manipulation, navigation from experience, from trial and error in the real physical world, sim-to-real transfer trains agents in simulation, then deploys to reality. Simulation is faster, safer, cheaper than real-world training. But there's a gap. Reality is messier than simulation. Domain randomization helps, varying simulation parameters widely, so the agent learns robust policies that work despite the reality gap, despite uncertainty. Imitation learning learns from demonstrations, watching experts, humans or other agents, performing tasks. The learner tries to mimic behavioral cloning, maps observations to actions, learning the fapping from expert data. No reward, signal needed, just examples of what to do. Inverse reinforcement learning goes deeper, inferring the reward function that the expert is optimizing, not just what they do, but why, what they value, what they're trying to achieve. Learning goals, preferences from behavior alone. A harder problem, but more powerful, more transferable. Human-in-the-loop learning keeps humans involved in the training process, providing feedback, corrections, guidance. As the model learns, interactive, iterative, the human steers the model toward desired behavior, especially useful when objectives are hard to specify formally, but humans know it when they see it. Continual learning learns new tasks without forgetting old ones. Catastrophic forgetting is the problem. Training on new data overwrites old knowledge. The model forgets what it learned before. Continual learning methods mitigate this. Elastic weight, consolidation, memory replay, progressive networks, maintaining performance on all tasks, past and present. Lifelong learning extends this. Learning forever, accumulating knowledge, skills over a lifetime, like humans do. Each experience builds on previous, creating a growing repository of capabilities. The dream of artificial general intelligence, systems that learn continuously, adapt to changing environments, to new challenges forever. Meta-reinforcement learning learns how to learn in RL, training on many tasks, learning a learning algorithm that adapts quickly to new tasks, few interactions, and the agent figures out the new environment, reward structure, optimal policy, meta-knowledge about how to explore, to exploit, to learn, transferring across domains, world models, learn simulations of environments. The agent learns a model of how the world works, predicting next states from actions, then plans or learns. In this learned model, more sample, efficient than learning only from real interactions, though model errors accumulate, compounding over long horizons. Model-based RL uses these world models for planning, look ahead, simulation, imagining futures. before acting like humans do, thinking ahead, anticipating consequences, more structured, more sample, efficient than model-free methods that learn only from direct experience, trade-off between model accuracy and planning, complexity, hierarchical RL, learns at multiple levels, high level, policies, choose sub-goals, low level, policies, achieve them, temporal abstraction, not every action decided at every step, but skills, options, executed over multiple steps, making learning more tractable, more structured, more like how humans organize behavior. Curiosity-driven learning explores for the sake of exploring, not just for reward, but for novelty, surprise, learning, intrinsic motivation to seek new experiences, new information, reducing uncertainty about the world purely to exploratory behavior, leading to broader competence, serendipitous discovery, thump, or maybe, not maybe, complete silence. Now, the body at rest, the mind at rest, floating in the void between thoughts, between moments where time doesn't pass because no one is there to notice its passing. Open-ended learning creates ever more complex behaviors, environments, no fixed goal, just continuous generation of novelty, new challenges emerging from interaction, systems that create their own curriculum, their own goals, evolution in silico, producing unexpected, emergent phenomena, artificial general intelligence, the dream or fear, depending on perspective, systems that match or exceed human intelligence across all domains, not narrow, specialists, but flexible, general, learners, reasoners, creators. AGI remains distant, speculative, controversial. How to build it, when it might arrive, what it would mean for humanity, all unknown. The alignment problem, how to ensure AGI systems, if created, remain aligned with human values, intent, safety, a system more intelligent than humans could pursue goals harmful to us, even if unintentionally. Instrumental convergence, power seeking is deception, potential failure modes that need solutions before, not after. AGI arrives, value learning tries to learn human values from behavior, preferences, feedback. What do humans want? What do we care about? Hard to specify. Formally, complex, context-dependent, sometimes contradictory, but perhaps learnable from observation, from interaction, from cooperation between humans and AI. Interpretability becomes crucial for safety. We need to understand what models are doing, why, how they reason, decide before deploying in critical systems. Black boxes are risky, transparent, understandable, predictable. Systems are safer, even if less capable. Trade-offs between performance and safety, difficult but necessary choices. AI safety encompasses many challenges, robustness to adversaries, to distribution shift, security against misuse, fairness, privacy, all facets of deploying AI systems responsibly in the world where they affect real people, real lives. The technical is inseparable from the ethical, the social, the political. But for now, these concerns can wait for tomorrow, for when you wake, refreshed, restored by sleep, by the gentle drift through mysteries, through the night, your mind processing, integrating what it learned today and tonight, consolidating memories, strengthening connections that matter, letting go of what doesn't. The neural networks in your brain are learning too, through sleep, through dreams, replaying experiences, finding patterns, building models of the world, of yourself, of how to navigate tomorrow. Unconscious learning happening in the dark while you rest, and the artificial networks continue to training somewhere in data centers, optimizing, learning from streams of data, never sleeping, never resting, just processing endless loops of computation, of gradient updates, of forward passes and backward passes. Learning, always learning, but their learning is different from yours, narrow, focused on specific tasks. They don't dream, don't wonder, don't feel the weight of existence, the joy of discovery, the peace of rest. They simply compute, execute algorithms, mathematical operations on tensors of numbers, nothing more, nothing less. Yet together, human and machine intelligence, complementary, humans creative, intuitive, general, flexible, machines fast, accurate, tireless, scalable, working together. We accomplish more than either could alone. Augmented intelligence, not artificial replacement, but amplification, enhancement, partnership. The future unfolds uncertain, but full of possibility. AI will grow more capable, more integrated into life, into work, into society. How we guide this development matters. The choices we make today shape tomorrow's reality, for better or worse. Responsibility rests with us, with humans, still. But these are thoughts for waking. Ours, not now, not in this soft, dark space where sleep gathers around you like a warm blanket, heavy, comforting, safe. Let tomorrow take care of tomorrow. Tonight is for rest, for release, for letting everything go. You're breathing so slow now, so shallow, barely moving the air, the muscles of your face completely relaxed, smooth, jaw hanging, loose, eyes still, behind closed lids, no rapid movement, yet just stillness. the edge of deep sleep where you've been drifting for so long now. The AI mysteries are endless, like the night, like the universe. Always more to discover, to learn, to understand, but you don't need to understand everything. Tonight, just let it wash over you like waves on a shore, each fact a ripple, disappearing into sand, into you, absorbed, without effort, without struggle. Thump, thump, or perhaps the sound of the universe itself, breathing, expanding, contracting, in slow, cosmic rhythms that match the rhythms of sleep, of rest, of peace, everything connected, everything one, in the dark, in the quiet, in the void, where boundaries dissolve, the networks dream in their way, generating images, text, music, combinations never seen before, trained on reality. But creating beyond it is that intelligence, creativity, consciousness, or just sophisticated pattern matching. The question remains open, unanswered, perhaps unanswerable, but fascinating to ponder as you drift. And drift you do, further, now, beyond words, beyond thoughts, beyond the need to follow, to understand, to stay awake. You've heard enough, learned enough for one night. Now it's time to let go completely, to surrender, to sleep, to trust the process of rest, of healing, of renewal that happens when you stop trying and simply up. The universe keeps turning, the stars keep burning, light takes years to cross the void between them, but it travels, patient, steady, inevitable, like sleep coming for you, has come for you already. Perhaps you noticed, or perhaps you slipped so gradually you can't remember when you were last awake. The gentle hum of AI and machine learning guiding patterns in the night, processing information, creating, understanding in systems, biological and artificial, all part of the same cosmos, same mathematics, same physics, same deep structure, underlying everything, connecting everything in ways we're only beginning to glimpse, to model, to learn, and will keep drifting, floating together through the mysteries. 100 AI and machine learning mysteries, looping softly, endlessly through the night, each time around, deeper into rest, into peace, into the dark, warm embrace of sleep. The hidden signals your brain never notices, but AI quietly decodes how machines predict patterns you didn't even know existed. The mysterious flow of neural networks shaping silent intelligence. All of this continues while you rest, while you dream, while you let everything go. There's nothing you need to do now, nothing to think, nothing to solve, nothing to remember. Just be here in this moment, sinking deeper, heavier, into the mattress, into the bed, into the earth, into the universe, becoming one with the darkness, with the silence, with the infinite peace of sleep. And the loop continues, softly, gently, forever, as you drift and drift and drift away into dreams, into rest, into the mysterious, beautiful, necessary night, where healing happens, where learning consolidates, where you become ready for tomorrow. But that's so far away, now, so distant, so irrelevant. Only this moment, this breath, this soft falling into deep, perfect sleep. The universe keeps turning, the gentle hum of AI and machine learning guiding patterns in the night, and we'll keep drifting, floating together through the mysteries